let's start by drawing a potato. And this potato is in the current configuration. And on this, so our potato is like a three-dimensional body, right? I'm drawing it two-dimensional. So if we take a little different, infinitesimally small area, and we assume that there's some force that acts on that area, these surface forces we call tractions. Anybody heard that term before? Tractions?
Yes.
Yeah. Well, you've taken continuum mechanics. Yeah. And of course, so they have units of force per unit area. It's a traction vector, right? Force per unit area, but it's a vector. Force is a vector, right? And also, if you considered some infinitesimal cube inside the body, then you could have body forces that act on it, and the most common one is gravity, right? So these are called body forces. You can also have body forces that arise from electromagnetics, but the most common one that affects everything is gravity. Right? So what I'm going to do, it's going to take a little bit to draw this correctly. What I'm going to do is I'm going to take that little cube and I'm going to pull it out and plop it onto a coordinate axis. Dang it. So this is x1, x2, x3, again in the current configuration. And then what I want to draw is each of these faces are going to be defined or have a unit vector, an outward pointing unit vector normal to the surface. And then likewise, we're going to draw those tractions on there, but we're going to identify that the traction vector, we're going to call this the x2. We're going to call this x2 just to indicate that it's pointing out of the face that's also in the x2 direction. Okay. And likewise, there'll be one x3 and x1. And just to be clear, like, you know, each of these traction vectors is a vector, right? So even, you know, each of these has 3 components. T1 and the X1, T2 and the X2, T3 and the X3. All right, so a couple of things. So just to clarify that, and then also to clarify here, these unit vectors, the traction vectors are not necessarily in the direction of the unit vector, right? I think I drew that, it's clear from the way I drew it. The other thing is, this thing is in equilibrium, so on every opposite face, there's an equal and opposite traction vector. So I'm not drawing in there because it's kind of busy, but because it's in equilibrium, there's an equal and opposite traction vector there. So now what I want to do is I'm going to take a plane sliced diagonally across the cube to create a like a hexahedron, octahedron actually. So it's going to be something like so this includes this plane that slices diagonally through the cube, but and also the back surfaces, right? What did I call it? It's a tetrahedron. Right? So now I'm going to try to redraw that little tetrahedron, okay, on a set of coordinates over here. So we're going to just focus on that tetrahedron. And so this this front face of the tetrahedron, we're going to say it has an area ds. It has an outward normal vector. So this is again normal to this surface, n. There's a traction vector T corresponding to the n face. Okay, again, not necessarily normal to n, or collinear. And then there's all the traction vectors that were on the back side of the cube, right? Because again, I drew the front side ones, but I said there's equal and opposite ones on the back side. So now we're going to attempt to draw those. Okay. So on the back side, there's a traction vector T x2 Over here, there's one T x1, and down here there's one T x3. All right. So remember what I said earlier? Whenever you don't know what to do, write down F equals MA. So let's write down F equals MA. We're writing the forces that act on this tetrahedron. So the sum of the forces is equal to T of N ds minus T x1 into ds. I'll come back to that, where that n2 comes from. Minus T x2. Let's see, this is x2, x3, n3 ds minus T x1 n1 delta s. And that's equal to the density times 1/3 the height, where the height is like this distance from this face down to the origin. Like that's the height, times delta S. All right. So this is the formula for the volume of a tetrahedron, right? If you know the area of this surface and you know the height, then the volume, right? Times acceleration, right? So we're trying to write MA over here, right? So density times volume gives you mass times acceleration, right? So on the right-hand side, MA. On the left-hand side, you might wonder where this like ds in 3 comes from. And what that is like if you have a say a line segment L with an angle theta, if you project that down onto this axis, what this is, if this is L, then what's projected down onto that axis is L cosine theta, right? So that actually same idea holds if you have a surface and you're projecting that surface down onto that plane. So if you had a surface A and you're trying to project it down onto, the plane, the underlying plane, then that would be like A cosine theta, right? Well, if you have a unit vector n, and if you compute like the cosine between n and x1, that gives you n1. And likewise, cosine between n and x2 gives you n2, and the cosine between n and x3 gives you n3. So basically what we're doing is we're taking that delta S and projecting it to get those other 3 areas via the direction cosines and the unit vectors. So we don't know the angle, but it's the angle between, you know, I'm not drawing theta, right? But it's the angle between the unit vector n and the x3. Whatever that angle is, that gives you the n3 projection, right? And so, and then that same projection holds, like I can project this down onto the x3 axis to get that on the back side, right? Okay. So now I have this equation, and all the, you see there's a delta S in everything, so I can cancel those. All right. Then take the limit as h goes to 0, because we're talking about an infinitesimal tetrahedron. So we're going to take the limit as h goes to 0, and then this side of the equation goes to 0. Yeah.
So h is the distance from the front surface to the vortex, or
Yeah.
from? Okay.
Yeah. From the surface, like straight down
To
the unit vector,
Okay.
the normal unit vector, straight back into the vertex.
Okay.
Yeah, that, and then this is just the formula for the area of a tetrahedron. Volume of a tetrahedron. If you know the area of the surface, this is the formula for the volume of a tetrahedron.
Okay, so that point should be at the middle of the front surface of
Yeah.
the tetrahedron.
Yeah, yeah. So take the limit as h goes to 0, the whole right-hand side goes away. Right? So now I just have essentially f equal to 0. So then I have, rearranging the equation, I have t of n is equal to t of x1 n1 plus t x2 n2 plus t x3 n3 Remember our, by default, if I don't say any different, like a vector is a column vector, right? So this is a column vector, that's a column vector, that's a column vector, right? I'm going to take the transpose of both sides of the equation. So then I have T could okay, so this is just writing that in matrix or vector form. Okay, but understand these are, since I transpose these vectors, now they're row vectors, right? So this is like row vector, row vector, row vector, all stacked on top of one another. So you got like in each component there's three directions. So there's three components here, three components, three components. So this thing is like a matrix or a tensor, right? And this thing is what we call the Cauchy stress. And we typically use the symbol sigma for that. And so we have T transpose is equal to NT this is the Cauchy stress formula, right? Or we can take the transpose of both sides of the equation and you get that, right? So then sometimes, because Cauchy stress, as we'll see later, is symmetric, then sometimes you'll see that dropped. But technically, the transpose is, because if it's symmetric, then it is its transpose, right? Any matrix that is symmetric, the matrix equals its transpose. So sometimes you'll see that dropped off of there. But is there a question?
Why do you think h tends to 0 there? Because it's a plane?
Well, because it's an infinitesimally small tetrahedron.
Okay.
Yeah.
And first of all, we made that tetrahedron by drawing the planes, right?
Hmm?
The traction,
Yeah.
just by drawing the planes. Then why are we considering the reaction tractions equilibrium force equation? Like we basically drew the
So the first thing is, right, we pull like a little cube out of a body that's subject to surface tractions. Any body that's subject to surface tractions is going to have forces on it. You know, if you pull out a little cube out of the middle of it, there's going to be forces on it, and if it's in equilibrium, they'll be on all sides, right?
Yeah.
So we pull that cube out here, and we write down the traction vectors on the cube, which again arise due to tractions on the surfaces, okay? Then we just take it a step further, slice that cube, and then take those same tractions, but they're on the back side, right? I just didn't draw them over here. This traction has an equal and opposite traction back there, right? So then we draw those on the front side of the cube, but if in order for the thing to be in equilibrium, right? If the thing is in equilibrium, then and there's a traction on the back side of all those cubes, there has to be an equal, one that equals on the front side of the cube, right? For it to be in equilibrium. And then we just write down F equals MA. And I mean, this traction on the front side of the cube is just by definition, because we drew a normal vector out of there, and then we call it Tn. Right? It's just like the generic traction vector. So Yeah, so Cauchy's stress equation maps, basically the Cauchy stress takes a normal vector and maps it into a traction vector, right?
If it was defined as a stationary object, the acceleration would still make it 0.
Yeah, you could have just wrote F equals 0. Yeah, because I think I said it was in equilibrium.
Yeah.
The equation holds. I think I said it's in equilibrium, but it holds if it's not, right? Because we wrote F equals ma, right, for an infinitesimally small octahedron, right? So, just a couple more things here today. Yeah. So I'm just going to label this Cauchy stress equation. In digital notation, it would be like Ti equal to sigma Ji in J. Because, so typically when we write a matrix vector product, we contract over the outer indices, right? So normally it would be sigma ij in J. That implies a matrix vector product, a normal matrix vector product, right? But if I transpose the indices such that the contraction, the summation, is over the inner indice, then that represents the transpose of the matrix, or tensor, right? And so if we write it out in component form, if we're using, 1, 2, 3 for our basis vectors, E1, E2, E3, two, or, sometimes if you're just using X, Y, and Z for your bases, you'll see it like this. So then, to be clear here, if we have our little cube, x1, x2, x3, this vector here would be so the convention here, the naming convention is that the first indice indicates the face. So the first indice indicates the face that it's acting on, defined by the coordinate system essentially, and the unit vector coming out of that face. And then the second coordinate is the component, right? So all these have the leading 2, 2, 2, meaning it's acting on the into face, and then it's the 1, 2, 3 component of that. I think we'll end a little bit early today. I'll stop there. Any questions? Has anybody seen that Cauchy stress equation derived before? Yeah. I mean, it's pretty standard. Every elasticity book or continuum mechanics book would have a derivation like that.